Alpha Centauri is the nearest stellar system to the Sun. Its light arrives in a little over 4 years. A spacecraft moving at Voyager 1's present speed would need roughly 75,000. That is the answer. 4 light-years is close for stars, not for machines. There is one hopeful footnote. Engineers have proposed tiny sails that light might push across the gap in about 20 years. They would weigh grams, carry no people, and flash past without stopping. No such interstellar mission is ready to launch. The shortest honest answer is still that humanity cannot go there yet. This is a place for anyone who likes science after the room grows dim. A subscription helps more night owls find it. No pressure. Cosmic Tide keeps the wide-awake version of the same wonder nearby. Nothing tonight needs to be remembered. Sleep can take any paragraph and leave the rest turning on its own. The night will move through distance, engines, sails, human bodies, and the worlds waiting at the other end. It starts with a small number that behaves much larger than it looks. The number is 4.25. It fits neatly on a page. A decimal point and only a few digits give it excellent manners. The distance behind it is less cooperative. A light year is the distance light covers in 1 year. Light moves through empty space at almost 300,000 kilometers each second. In 1 second, it could circle Earth more than 7 times. Across 1 year, it crosses nearly 9.5 trillion kilometers. The name occasionally causes a small filing error in the mind. A light year measures length, not duration. The year belongs to the ruler because light supplies the measuring tape. Nothing in the unit promises that a spacecraft can cover it in a year. Even light needs time to make the crossing. The Alpha Centauri seen tonight is already a historical addition. Any change occurring there now will remain unknown on Earth until the middle of the decade has turned again. Multiply that just beyond 4-fold. The result is about 40 trillion kilometers. Miles make it roughly 25 trillion. Both numbers are correct, and neither settles easily into a human room. A smaller model helps. Suppose the span between Earth and the Sun were shortened to one school ruler. Earth would rest at one end. The Sun would glow at the other, 30 centimeters away. On that scale, Neptune would be about 9 meters from the Sun. The nearest star would not be in the classroom. It would not be in the school. Proxima Centauri would sit about 80 kilometers away, somewhere beyond the next town. The whole solar system would occupy one end of a building, while the next stellar address waited in another city. That is why the usual picture of neighboring stars can be misleading. Star charts place bright points close together because paper is finite. The sky also flattens depth into a dark dome. 2 lights can appear side by side, while one is trillions of kilometers behind the other. Earth's own orbit helps restore that missing depth. Nearby stars appear to shift slightly against more distant ones as the planet moves around the Sun. Astronomers call the effect parallax. The angle is tiny, yet it turns a point of light into a measured address. Alpha Centauri looks nearby in photographs of the southern sky. In stellar terms, it is. The galaxy is about 100,000 light-years wide. Against that immense diameter, 4 light-years is a short gap between houses. Human machines live on another scale. Voyager 1 has traveled farther from Earth than any other working craft. It moves relative to the Sun at about 17 kilometers each second. That is enough to cross a large city before a kettle begins to warm. At that rate, a straight trip to Proxima would last around 75,000 years. Voyager is not heading there, so even that is only arithmetic. The calculation simply borrows its speed and points an imaginary copy toward the star. 75,000 years reaches beyond every city now standing. It reaches past farming, writing, and the first permanent villages. A craft launched when early humans were shaping stone tools would only now be preparing to arrive. The machine would need to work for that entire span. Its power source would have to last. Instruments would need protection. Navigation would have to remain accurate after languages, countries, and perhaps coastlines had changed behind it. The distance has another quiet trick. Traveling there is not the same as sending a message. A radio signal already moves at light speed. If one left Earth tonight, it would reach Proxima after just over 4 years. A reply would take the same time coming home. That makes the nearest possible conversation an exchange measured in childhoods. A simple question and answer would occupy roughly a child's first 8 years and 6 months. Nobody forgot to install faster mail. The universe supplied no faster service. Raise the speed, and the gap becomes clearer. 1% of light speed sounds heroic. It is nearly 3,000 kilometers each second, far beyond any spacecraft built so far. Even then, the crossing takes more than 4 centuries before acceleration or braking are counted. At 10% of light speed, the coast alone lasts about 42 years. That begins to fit inside one human lifetime. It also demands an engine, fuel supply, shield, habitat, and braking system unlike anything now in service. At 20%, a very small probe could cross in a little over 20 years. That is the promise behind laser sail studies. It is also where grains of dust become engineering events. Communication becomes delicate, and stopping at the destination becomes a separate mission. So the title's question closes early. Alpha Centauri is not hidden. The route is not unknown. Moving matter through 40 trillion kilometers of space carries the real price, along with keeping it intact, useful, and slow enough to arrive. There is no shame in the answer. A century ago, no machine had visited another planet. Today, instruments work beyond the sun's protective bubble. Progress is real. The gap simply remains larger than the word nearest suggests. That word belongs to astronomy. Reachable belongs to engineering. Between them lies one of the calmest facts in the night sky. The closest other suns are visible, measurable, and still very far away. For now, their light makes the crossing alone. It leaves 3 stars, travels 4 quiet years, and settles on Earth without needing fuel. The small, bright point arrives every night. Machines are allowed more time. Alpha Centauri is one name for a family of 3 stars. The name sounds singular because the unaided eye blends the system into one bright point. Astronomy enjoys giving a household one label and several proper names. then leaving everyone to sort the post. The two brightest members are Alpha Centauri A and Alpha Centauri B. They are also called Rigil Kentaurus and Ptolemy. Both resemble the Sun more closely than Proxima does. Alpha Centauri A is a yellow star of the same broad type as the Sun. It is a little larger and brighter. Alpha Centauri B is slightly smaller, cooler, and more orange. Together, they form a binary pair. The two stars orbit a shared center of mass. One circuit takes about 80 years. Their distance from each other changes through that long ellipse, moving from a little beyond Saturn's scale to well outside Neptune's. No material bridge joins them. Gravity is enough. Each star follows the curved path written by the other's mass, and the pair has kept that appointment for billions of years. From a suitable planet, the sky could hold two suns. Their apparent separation would change slowly across a lifetime. Some years might bring two distinct daylight lamps. Other years would draw them closer together. There is no confirmed Earth-like world around either member of the bright pair. A recent telescope result has made that sentence more interesting, but not yet obsolete. James Webb found a candidate near Alpha Centauri A. It will have its own unhurried place later tonight. The third star is the one that wins the distance contest. Proxima Centauri lies slightly closer to the solar system than A and B. Its name comes from the Latin word for nearest. Proxima is a red dwarf. It holds only about an eighth of the Sun's mass and releases a tiny fraction of its visible light. Despite being the nearest star beyond the Sun, it cannot be seen with unaided human eyes. That is a pleasant correction to the idea that closeness guarantees brightness. A distant lighthouse may outshine a nearby candle. Proxima is the candle, though it occasionally develops a rather energetic opinion about ultraviolet light. The red dwarf sits far from the central pair. It is gravitationally bound to them on an orbit so wide that one circuit takes more than 500,000 years. Alpha Centauri A and B complete thousands of their own dances during one slow turn by Proxima. On the ruler model, this stellar family would occupy a region far larger than the solar system model back at school. The members belong together, yet they do not crowd. Space has never shown much enthusiasm for cramped housing. Astronomers spent years testing whether Proxima truly belonged to the other two. The stars share motion through the galaxy, and careful velocity measurements support a bound orbit. Together, they form a hierarchy rather than a tidy little triangle. Alpha Centauri A and B hold the center. Proxima travels around them at great range. Planets then circle at least one of those stars, producing smaller clocks within the larger ones. Each member also ages at its own pace. The bright pair burns hydrogen quietly in a manner broadly familiar from the Sun. Proxima spends its fuel far more slowly, so red dwarfs can remain steady for immense stretches of time. Its surface is cooler, yet magnetic fields can store and release fierce energy. A dim star need not be an inactive one, or a simple neighbor for a planet. 2 planets around Proxima are confirmed as of tonight. Proxima b is roughly Earth mass and completes a year in about 11 days. Its smaller neighbor, Proxima d circles even closer and finishes an orbit in about 5 days. A proposed outer world called Proxima c remains a candidate. Some earlier summaries treated it more firmly. Newer measurements have not supplied the peer-reviewed confirmation needed to promote it. A candidate is an invitation to keep measuring, not a planet to count early. Careful counting still wins. The distinction matters because the system is difficult to observe. Proxima's magnetic activity can place signals inside the same data used to find planets. A star spot turning with the star may imitate part of a planet's pull. Researchers separate those rhythms by collecting years of precise spectra. They watch tiny shifts in the star's light as gravity moves it toward and away from Earth. The motion can be slower than a person walking. Alpha Centauri A and B create different problems. They are bright, close together in the sky, and always changing position. Their glare can bury the faint warmth of a planet millions of times dimmer. The system is close enough to reward the effort. A world there offers better chances for future study than a similar planet hundreds of light years away. More light arrives. Angular separations are larger. A probe, if one ever crosses, faces the shortest available interstellar road. Shortest does not mean simple. Proxima's orbit carries it around the main pair across a span of deep time. The exact three-dimensional arrangement changes. Any future navigator would need to predict where every star and planet would be decades after launch. That prediction is possible. Celestial mechanics is patient mathematics. The difficulty is not finding the address. It is delivering the envelope to a house that keeps moving while the courier spends a generation on the road. Seen from Earth, Alpha Centauri's light is already old by a little more than 4 years. The system visible tonight is the system from 4 summers ago. This delay is small beside most astronomy, where telescopes routinely look millions or billions of years backward. For a destination, it feels different. Mission planners would always navigate toward a future position using an image from the past. They would calculate the orbit forward, then aim at where the family will be. The same practice guides ordinary probes inside the solar system. Mars is never targeted where it appears at launch. A spacecraft heads toward the place Mars, and the craft will meet. Alpha Centauri adds more distance, more motion, and a calendar with heavier pages. The 3 stars continue regardless. Meanwhile, the bright pair completes its 80-year turn. Farther out, the small red companion advances along an orbit too long for any civilization to watch in full. Their clocks nest together, steady and unconcerned. That is the destination before any engine is chosen. Not one lonely star, but a spacious family. 3 suns move through the dark, carrying at least 2 confirmed planets, and one especially interesting question mark. Humanity's speed record belongs to a craft that keeps falling toward the sun. Parker's solar probe reached about 430,000 miles an hour during its closest passes. Nothing made by people has moved faster. The number is often carried straight into interstellar comparisons. Divide the distance to Proxima by Parker's speed, and the answer is roughly 6,500 years. That arithmetic works. The mission does not. Parker gained that velocity through an oval solar orbit. 7 flybys of Venus gradually reshaped its path. Near the Sun, gravity turns a very long fall into enormous speed. Then the probe climbs away again. It gives much of that speed back, while rising through the Sun's gravity. Parker cannot simply turn at perihelion, keep the full record, and point toward Alpha Centauri. A downhill racing bicycle may cross the finish line quickly. Asking it to preserve that speed up the next mountain changes the story. Parker's record comes with a steep hill and a star-sized footnote. The craft was built to study the solar corona. Its heat shield passes within a few million miles of the visible surface. The front grows hot enough to challenge metals, while the instruments remain shaded behind it. That achievement is extraordinary on its own terms. It does not need an interstellar assignment to become impressive. Parker measures fields, particles, and the solar wind where they begin. The more useful comparison for an escaping spacecraft is Voyager 1. Launched in 1977, it used Jupiter and Saturn to gain speed and leave the planetary region. In 2012, it crossed the heliopause, where the solar wind gives way to interstellar space. Voyager now moves near 17 kilometers each second relative to the Sun. It is not heading for Alpha Centauri. Its path points elsewhere through the galaxy, where it will pass other stars only after tens of thousands of years. The probe still speaks to Earth. Its radio arrives as an extremely faint whisper, gathered by the large dishes of the deep space network. Commands and replies take most of a day each way now, not 4 years. Even that delay has changed operations. Engineers plan carefully, because a quick correction cannot be quick. They send instructions, wait through a long stretch of silence, and learn later whether an old machine understood. Voyager's speed feels large close to home. It could travel from London to New York in a few minutes, if oceans and atmosphere politely stepped aside. Across a light year, the same pace becomes almost still. This is not because the craft slows in interstellar space. It will coast for ages with little resistance. The destination is simply so far away that a constant high speed produces a very long calendar. Spacecraft speed also depends on the chosen frame of reference. Parker's record is usually quoted relative to the Sun near perihelion. Voyager's escape rate is heliocentric as well. A different observer moving through the galaxy would measure different values. Mission comparisons, therefore, need matching frames and matching kinds of motion. A peak speed for a few hours near the Sun is not the same as a cruise speed sustained between stars. Records are useful. Their fine print is useful too. Direction matters alongside speed. A probe cannot turn like a car because empty space offers no road for its wheels. Engines must change the whole velocity vector, and every change spends propellant or borrowed gravity. Even a perfectly aimed departure begins as a carefully shaped curve out of the solar system. Only later does the long interstellar coast become almost straight. Escape speed is not one fixed number everywhere. It falls with distance from the Sun. A craft leaving the inner solar system spends energy climbing the same gravitational slope that made Parker fast on the way down. Gravity assists do not create energy from nothing. A probe takes a minute amount from a moving planet's orbit. The planet slows by an immeasurably small share, while the lightweight visitor leaves with a useful change in direction and speed. Chemical rockets create their greatest speed changes while fuel is burning. Afterward, a probe usually coasts. Gravity assists can redirect motion and borrow energy from a planet's orbit, but the exchange is tiny for the planet and valuable for the craft. Voyager used that method beautifully. Jupiter and Saturn supplied moving gravitational slopes. The probe entered each encounter one way and left another, taking a small share of orbital energy with it. There are no waiting planets in the empty distance after Neptune. An interstellar craft cannot count on a chain of convenient giants all the way to Proxima. Most of the crossing offers nothing massive enough to provide another push. The sun can help at departure. A craft might dive close, gain speed, and add thrust, or unfold a sail where sunlight is strong. Yet it must still leave the sun's gravity with the desired excess velocity. That last phrase matters. Excess velocity is what remains after the climb. Parker's headline number is not what remains. An interstellar design must budget for the speed carried into the dark, not merely the speed borrowed at the bottom. The current record and the current escape rate teach different lessons. Parker shows how fast a small machine can move for a while. Voyager shows how slowly even a successful escape crosses a stellar distance. Coasting is quieter by comparison. Both machines are modest in size. Neither carries the food, water, shielding, engines, spare parts, or living space required by people. Adding mass makes every future speed increase more expensive. That expense begins before the first kilometer. A rocket must accelerate its payload and its remaining fuel. More fuel adds weight, which requires more fuel, which adds more weight. The loop is mathematical and rather stubborn. There is an equation for it. It is short enough to fit on a chalkboard. Like the 4.25 on the star chart, it uses very little ink to describe a very large inconvenience. Voyager continues without concern for the chalkboard. Its small nuclear power supply fades gradually. One instrument after another will fall quiet as engineers save the remaining electricity. Long after the last signal, the craft will keep its solar orbit around the galaxy. The golden record will travel with it, protected by a cover and addressed to no scheduled recipient. Its message may never be opened. That is all right. Voyager's work was never to reach another sun. It showed that a machine could cross the boundary around this one. A wider boundary comes next, with its equation waiting. Behind every rocket waits an equation named for Konstantin Tsiolkovsky. He published his version in 1903. It explains how a vehicle gains speed by throwing part of itself backward. The idea is simple. Hot gas leaves an engine in one direction. The rocket moves in the other. Nothing pushes against the vacuum. Momentum keeps the accounts. The difficult part appears when the desired speed rises. A rocket must carry propellant for later burns. It must first accelerate that propellant along with its tanks, engines, structure, and payload. Add more fuel, and the starting vehicle becomes heavier. Extra mass then asks for still more fuel. As a result, the relationship is exponential rather than a neat row of equal steps. This is why ordinary rockets arrive on the launch pad mostly made of propellant. Reaching low Earth orbit already consumes nearly everything a single stage can sensibly carry. Staging drops empty tanks and engines along the way, which helps enormously. Yet staging does not repeal the equation. It divides one difficult climb into several smaller ones and discards hardware after its work is finished. Every new stage begins with less dead mass. An interstellar vehicle could use stages too, but each discarded engine was accelerated before release. Empty tanks still collected their fare for part of the journey. Breaking stages would collect another fare before waiting decades for their turn. The bookkeeping remains patient. Even discarded metal had to earn its place aboard before departure. Interstellar speed asks for far more. A good chemical engine throws exhaust at only a few kilometers each second. 10% of light speed is almost 30,000 kilometers each second. The mismatch is not close. It is not a matter of making one tank slightly larger. Placing those values into the rocket equation produces a mass ratio with more zeros than any physical design can use. That statement sometimes becomes a theatrical claim that the fuel would outweigh the universe. The precise number depends on the engine and mission. A calmer conclusion is enough. Chemical propulsion cannot carry its own way to a useful fraction of light speed. An engine with faster exhaust changes the result. Ion thrusters throw charged particles much faster than chemical gas. They use propellant efficiently and can keep pushing for a long time. Their thrust is very low. The gentle push suits robotic probes already in space. It does not quickly accelerate a shielded habitat weighing thousands of tons. Power becomes the next part of the bill. An ion engine needs electricity. Far from the sun, solar panels receive less light. A reactor can help, but the mass of the reactor and its cooling system joins the payload. Nuclear thermal rockets heat a light propellant in a reactor and expel it. They can improve on chemical engines. Their exhaust is still far too slow for a 40-year crossing to another star. Fusion promises a greater leap because light nuclei can release much more energy. Controlled fusion on Earth has made major experimental progress. Yet no fusion power plant supplies a grid. No flight-ready fusion rocket exists. Antimatter offers even more energy per unit mass. When matter and antimatter meet, their mass becomes other forms of energy. The reaction is efficient in a physics equation and exceptionally awkward in a storage tank. Humanity can produce tiny quantities of antimatter in laboratories. The process uses far more energy than the antimatter stores. Any useful supply would need electromagnetic containment that never failed. The equation does not dislike one engine brand. It simply compares desired speed with exhaust speed. Slow exhaust makes the starting mass swell. Fast exhaust demands difficult physics, difficult materials, or both. There is also a separate energy floor. Even a perfect drive cannot accelerate mass for free. 1 kilogram moving near 30,000 kilometers each second carries roughly 450 trillion joules of kinetic energy. That is enough to run a 1 kilowatt heater for more than 14,000 years. The comparison is gentle only because the heater is. Still, the energy has to be created, directed, and kept away from everything except the intended motion. A real engine wastes some energy as heat and radiation. The spacecraft must shed that heat. In vacuum, it cannot cool through air or water flowing past the hull. It needs large radiators glowing energy away. Those radiators add area and mass. They also face impacts from dust. Every system helps another system and burdens a third, which is how a small sketch becomes a starship. Speed is only half the required change. A craft that plans to stay must slow near Alpha Centauri. If it carries braking propellant from Earth, that propellant must be accelerated during departure too. The rocket equation notices this immediately. Mission art sometimes does not. A bright line reaches the target, the engine turns off, and arrival occurs with suspicious ease. Physics is less decorative. A craft passing at 1/10 of light speed remains fast enough to cross 1 astronomical unit in well under 2 hours. Without braking, the destination is scenery. This is why serious studies explore engines that do not carry all their reaction mass. Light can give momentum to a sail. A magnetic field might push against charged particles. An external beam can leave the power plant at home. Each method moves part of the burden somewhere else. One laser sail avoids onboard fuel, but requires an immense laser and delicate aiming. Magnetic braking avoids propellant, but needs a large, reliable field structure. The equation is not a locked door. Instead, it is a price list. Engineers learn which costs cannot be negotiated and can move the remaining ones into a form that might someday be paid. Beamed propulsion is one such move. A laser sail is not a rocket, so it does not carry the machinery that supplies most of its departing energy. The power plant, cooling equipment, and much of the mass remain near Earth. Momentum still balances. Photons change direction when they reflect from the sail, and the array receives the opposite reaction. No rule is escaped. The design simply keeps the heaviest side of the exchange at home. That move helps tiny payloads more than towns. Scale a wafer into a habitat, and the sail, beam, and pointing system grow with it. The equation has not returned, but the engineering bill has found several new envelopes. Tsiolkovsky never saw a rocket reach orbit. His compact formula did. It now sits inside every launch plan, quietly reminding even the boldest starship that fuel must be carried before it can be spent. Long before anyone found a planet around Proxima, engineers were drawing machines for the space between stars. The drawings were serious. Those machines remained on paper, which has always been the least expensive place to store a starship. Project Orion began in the late 1950s. Its central idea was nuclear pulse propulsion. A large vehicle would release nuclear explosive units behind a thick pusher plate, one after another. Each pulse would expand against the plate and push the craft forward. Shock absorbers would turn the violent sequence into manageable acceleration. In principle, the method could move payloads far heavier than chemical rockets could manage. The design grew from work associated with Stanislaw Ulam and a team at General Atomics. Physicist Freeman Dyson later explored interstellar versions. Many Orion studies focused first on fast travel within the solar system. The attraction was thrust. A nuclear pulse carries enormous energy, and Orion could apply it to a massive ship. Its drawback was not hidden in small print. In practice, the vehicle advanced by setting off nuclear devices behind itself. Testing posed environmental and political problems. The Partial Test Ban Treaty of 1963 prohibited nuclear explosions in the atmosphere and outer space. Orion lost the path to full-scale development. The project did not fail because one equation exposed a simple mistake. It reached a boundary made from treaties, fallout, cost, and public risk. A technically imaginable engine still has to belong to a civilization willing to build it. Some later retellings assign Orion an exact trip time to Alpha Centauri. There was no single final interstellar vehicle with one settled performance. The family of designs ranged widely. It is safer to remember the principle and the scale. A different group began a more complete interstellar study. In 1973, the British Interplanetary Society called it Project Daedalus. Its destination was Barnard's Star, nearly 6 light-years away. Daedalus was uncrewed. It would use pulses of fusion rather than nuclear weapons against a plate. Tiny pellets containing deuterium and helium-3 were meant to ignite hundreds of times each second inside a magnetic engine. The design had 2 stages. It would accelerate for almost 4 years, discard the first stage, and continue until reaching a little over 12% of light speed. Then it would coast for about 46 years. The final science probe alone would weigh hundreds of tons. At launch, the vehicle and its fusion fuel belonged to the scale of large ocean ships. It was a spacecraft designed for an industrial solar system, not one launch pad. At the destination, Daedalus would not stop. It was a flyby. After half a century of preparation and travel, Barnard's Star would pass quickly, while autonomous instruments worked without help from Earth. That detail is easy to miss. The study solved one version of the mission by refusing the braking bill. It traded years of observation for speed and made a short encounter carry the weight of a long voyage. Daedalus also needed helium-3 in quantities unavailable on Earth. Its designers considered gathering the isotope from a giant planet's atmosphere. That fuel supply therefore required an off-world mining industry before the Starship could begin. Yet the fusion engine never existed. Neither did the pellet production system, the giant magnetic nozzle, or the autonomous repair capability. The study was not pretending otherwise. Its purpose was to ask whether an interstellar probe could be described without inventing new laws of physics. The answer was a qualified yes, provided an advanced society built an astonishing list of supporting industries. That qualification is the most useful part. Daedalus gave the dream mass, stages, heat, dust shields, computers, fuel, and a schedule. It converted a silver shape in a painting into thousands of engineering decisions. The proposed craft would release fusion pulses at a rate that sounds more like machinery than magic. It would carry spare systems, because no repair ship could follow. Its computers would have to navigate and observe after decades without an update from the people who launched it. The final report appeared in 1978. After 5 years of study, it examined far more than an engine. Teams considered structure, communications, navigation, scientific instruments, reliability, and protection from interstellar dust. That breadth made Daedalus a reference design rather than a launch proposal. Every subsystem had to agree with the others on mass, power, heat, and timing. A larger shield changed the engine budget. Stronger transmitters changed the radiator. Paper allowed those arguments to happen cheaply, which is one reason the study still appears in modern discussions. It offered later engineers a complete disagreement to improve, not merely a beautiful silhouette. The reference remains useful tonight. Nothing on paper entirely escaped the ledger. Daedalus would accelerate for nearly 4 years and coast for most of the mission. Its target would grow during the final approach, yet the probe's speed allowed no second attempt. Autonomous systems had to prepare every instrument before a flyby lasting only days across the broad stellar neighborhood. The design carried a heavy erosion shield at the front. It also considered releasing a cloud of fine particles ahead of the vehicle, so incoming dust would strike that material first. Even a paper starship learned to bring an umbrella for a sky with almost no weather. Those requirements remain recognizable. Modern concepts use different materials and smaller payloads, yet they still face power, autonomy, shielding, pointing, and communication. The old paper machine continues to ask good questions. Orion and Daedalus also reveal a useful split. Moving people and moving instruments are not the same task. A robot does not need air, food, gravity, or a town's worth of living space. Machines tolerate long silence better. They can be frozen, spun, folded, and launched, with acceleration no human body would enjoy. Such travelers are still difficult to send, but their difficulty fits inside engineering more comfortably. That is why the first arrival at another star will almost certainly be robotic. The earliest traveler may weigh less than a coin. It may carry cameras smaller than a fingernail and a sail too thin to survive a careless touch on Earth. The route from Daedalus to that tiny craft is not a straight line. It is a change in strategy. Instead of building an engine powerful enough to push a mountain, the newer idea makes the payload almost weightless and leaves the engine at home. Paper kept Orion and Daedalus safe from their harder materials. It also kept their questions alive. The next design begins with one of the oldest forces available: the pressure of light on a mirror. Light has no rest mass, yet it carries momentum. When photons reflect from a surface, they give that surface a tiny push. Sunlight already moves dust, shapes comet tails, and changes spacecraft orbits by small amounts. A solar sail turns that push into propulsion. It spreads a light, reflective sheet and lets the sun press against it. The pressure is weak, but fuel never runs out while light remains. Interstellar plans need a stronger lamp. Breakthrough Starshot proposes a large phased array of lasers on or near Earth. The beams would act together and focus on a sail attached to a gram-scale electronic craft. Attached to that sail, the object is less a ship than a very ambitious postage stamp. Its sail would be much larger than its computer. Cameras, sensors, power storage, navigation, and communication would all have to survive in a package measured in grams. The laser would push for only minutes. During that short acceleration, the sail might reach about 20% of light speed. It would then fold or coast through the dark for a little over 20 years. The project is a research program aimed at proof of concept. It is not a scheduled mission. Its official challenge list remains long, open, and admirably unembarrassed. That distinction matters. In 2017, prototype chips called Sprites reached low Earth orbit as secondary payloads. They were not interstellar craft and carried no laser sails. The flight showed that sensors, communication, and power can inhabit a device only a few centimeters across. That demonstration sits near the bottom of a long staircase. A Sprite in orbit does not prove a sail can endure 100 gigawatt class beam. It does make the phrase gram-scale spacecraft less imaginary than it once was. The system also has to launch through an atmosphere or operate from space. A ground array is easier to service, but must correct for moving air. An orbital array avoids weather and becomes a vast construction project beyond Earth. The beam itself must hold the sail with extraordinary precision. Earth's atmosphere distorts light. The planet rotates. Meanwhile, the sail accelerates away while the laser spot tries to remain centered on a target growing smaller by the second. An immense power supply would feed the phased array. Design discussions commonly place it on the scale of a large national electrical load, delivered for a brief interval. Generating the energy is only part of the work. Thousands of emitters must behave like one optical instrument. The sail must be reflective, light, and resistant to heating, absorb even a small fraction of the beam, and an ultra-thin material can warp or fail. It also needs to remain flat enough for the pressure to point in the intended direction. Beam width grows with distance because even carefully organized light diffracts. A larger array or shorter wavelength can hold the focus longer, though both bring new demands. During the final seconds of acceleration, the sail is far away and rapidly shrinking from the array's view. Optics must keep finding its center, while the atmosphere and Earth's rotation keep changing the path. The smallest steering error becomes a larger miss once the beam is gone. Acceleration would be fierce. A human crew would not be aboard. Electronics can tolerate forces that would turn a comfortable cabin into a very poor idea. The kinetic energy is considerable even at gram scale. 1 gram cruising at 20% of light speed carries enough energy to run a 1,000-watt heater for almost 60 years. The laser must provide more because no real system is perfectly efficient. Once the push ends, the probe has no bright engine plume. It coasts. The solar system shrinks behind it, and the sail may fold to reduce the area exposed to dust. Navigation becomes exacting. A small angular error at departure grows across 40 trillion kilometers. The target also moves during the 20-year cruise. Aiming requires a future appointment, not a current photograph. Star trackers can compare the sky with stored maps. Tiny photon thrusters may make small corrections. The craft must do this with limited energy and no helpful mechanic nearby. Moving at 1/5 of light speed, the probe cannot receive quick messages from Earth. Instructions still move at light speed, but the craft adds distance while they travel. By the later years, every command describes an old situation. Autonomy is therefore part of the propulsion system. The probe needs to recognize faults, choose observations, manage power, and point its instruments without waiting for permission. Its software becomes a distant crew of one. Arrival is another compressed word. The Starshot concept is a flyby, not an orbit. At that cruise rate, the craft crosses the radius of Earth's orbit in about 42 minutes. A planet would pass much faster than that. Cameras must find it, stabilize, expose, store data, and turn toward the next target during a brief encounter. 20 years of travel may lead to minutes of useful geometry. Then comes the quietest engineering problem. The probe has to send information home. A tiny laser signal must cross 4 light years and land near Earth, where large receivers try to separate it from the light of the stars. The sail itself may help focus the transmission. Energy could be stored slowly and released in short bursts. Even then, data rates would be modest, and the first images would begin arriving more than 4 years after they were taken. One probe may not be enough. Concepts often imagine a swarm, because small craft can fail. Many launches could spread risk, relay signals, and offer slightly different views of the target system. That turns reliability into statistics. A lost wafer is still a loss, but it does not end the mission. The flock carries what one delicate machine cannot. None of this requires faster-than-light travel. No new physical law is requested. The concept instead asks materials, optics, power systems, and microelectronics to perform near the edge of what anyone can build. That is why it remains credible and unfinished at the same time. The promise is real enough to study. Real obstacles remain strong enough to prevent a launch date. If it works, the first human-made object to reach another stellar system may contain less mass than a house key. It will not carry a flag or a footprint. Instead, it will carry a few instruments, a careful clock, and a very narrow beam home. Light will have pushed the craft outward. Its message will return on light. Between those two uses of the same old thing lies an entire generation of waiting. The space between stars is often called empty. That is useful at ordinary speeds. Near 1/5 of light speed, emptiness begins to feel like weather. Interstellar space contains gas, mostly hydrogen and helium, along with heavier atoms and tiny grains of dust. The density is extremely low. Each cubic centimeter may hold only a few particles, or fewer, depending on the region. Slow spacecraft can pass through that material with little notice. Relativistic probes meet the same atoms at enormous relative velocity. Energy rises with speed, and the leading surface receives every encounter. In the probe's frame, Ordinary hydrogen arrives like a beam of energetic particles. The atoms can implant themselves in material, disrupt crystal structures, and produce secondary radiation. Nothing is angry. The arithmetic is simply quick. Dust adds a different kind of damage. A microscopic grain carries many atoms together. On impact, it can melt or vaporize a small patch, leaving a crater where a surface had been smooth. This is sometimes described with one dramatic grain destroying the whole craft. Large grains are possible, and a direct strike could be serious. Their abundance along one narrow path is not known perfectly. The quieter threat is cumulative. Countless smaller collisions can sand the leading edge across 20 years. A published study of a probe cruising near 60,000 kilometers each second estimated surface erosion on the scale of 0.5 millimeter under its chosen dust assumptions. Gas damage in that study reached about 1/10 of a millimeter in quartz. Other materials behaved differently. Graphite looked more resistant, which is why a thin forward shield appears in several concepts. 0.5 millimeter is smaller than a credit card's thickness. On an ordinary vehicle, it sounds modest. For a gram-scale craft, built from layers thinner than paper, it becomes a large fraction of the design. The shield adds mass, and mass lowers the final speed for a given beam. Removing protection helps acceleration and hurts survival. The probe must be light enough to launch and sturdy enough to arrive. Shape can help. A narrow craft presenting a small frontal area meets less material. The broad sail may fold behind the shield during cruise, turning a shining square into something closer to a slim needle. Folding introduces hinges or flexible structures. Those pieces must work after intense acceleration. They must not trap heat, tear, or leave the communication system pointing the wrong way. Collisions also charge the craft electrically. Ultraviolet light can remove electrons. The charged probe then moves through the weak magnetic fields between stars and feels a small sideways force. Across a short distance, the deflection is tiny. Over 4 light years, tiny effects accumulate. A paper on relativistic nanocraft found that charging and magnetic fields could alter both trajectory and orientation. Dust impacts can add small torques as well. The probe may begin to rotate. Rotation changes which face receives damage and whether a camera can point during the brief arrival. Heating accumulates at the forward surface. Gas collisions and dust evaporation deposit energy in a layer that cannot be cooled by an airstream. The shield must conduct that warmth away or radiate it without softening the electronics behind it. Material choice changes the answer. Quartz, graphite, metals, and layered composites respond differently to implantation, melting, and cracking. The best optical sail is not automatically the best cruise shield, so the craft may need both. Large grains remain a statistical uncertainty. A survey cannot count every speck across the route. Sending a swarm, narrowing the frontal area, and mapping the local cloud are ways to make uncertainty smaller without pretending it disappears. Grain size matters as much as grain count. Tiny particles are numerous and wear surfaces gradually. Bigger ones are rarer and deliver their energy to one small place. A shield designed for steady erosion may respond differently to a deep local crater. Layered material can spread heat and keep one damaged face from becoming the whole vehicle. The path is also long enough for probabilities to matter. No map can promise a clear corridor, molecule by molecule. Mission design therefore combines observation with margin. Several thin defenses can be more useful than one brave sheet expected to survive every possible impact. Quiet redundancy belongs at the bow. Engineers can respond with attitude control, conductive paths, shielding, and better maps of local interstellar material. None is a single complete answer. Together they turn the crossing into a manageable research program. The route itself can be studied before launch. Astronomers observe the absorption of nearby starlight to estimate gas and dust along different directions. Probes inside the outer solar system can measure the local medium more directly. The local neighborhood is not uniform. Within it, the sun sits inside a region of thin, warm gas called the local interstellar cloud, within a larger low-density cavity. A path toward Alpha Centauri samples its own particular mixture. That makes one route safer than a generic average and perhaps less safe than another. A starship cannot assume the whole dark has one forecast. The first interstellar mission may need a weather report made from spectra. Launching many small probes offers another protection. Their paths can be separated slightly. A dust grain that meets one should miss the others, and the surviving craft can compare what each encountered. The swarm could also send reports during cruise. Each little signal would describe the gas, field, charge, and impacts along the way. Later probes would inherit a map made by the first. Human missions face the same medium with far more surface area. Their lower proposed speeds reduce impact energy, but their journey lasts longer, and their hull must protect living tissue. Shielding cannot be an afterthought attached to the front. At 10% of the speed of light, even sparse hydrogen becomes a source of heat and radiation at the bow. A thick water layer or stored supplies could help protect the habitat. Active magnetic shielding remains an area of study. There is no need to turn the crossing into a storm. Most of it would look perfectly still. No grains would streak past a window. The danger lives in small events too fast and faint for human eyes. A forward shield would take them quietly. Its surface would change atom by atom, crater by crater, while the stars ahead barely moved. Maintenance might mean rotating panels or exposing fresh material. After 20 years, the leading edge would carry a record of the route. It would be a map written as where. The emptiness between stars would have left its handwriting after all. Reaching a star and staying near it are two different missions. First comes speed. Staying requires losing that speed again. An object in motion will continue unless a force changes it. Interstellar space offers almost no natural drag. A fast probe does not ease gently into Alpha Centauri like a boat entering a harbor. At a fifth of light speed, one astronomical unit passes in about 42 minutes. Alpha Centauri A and B would swell from bright points into suns, then slide behind. the encounter would be over before an ordinary film finished. That can still produce valuable science. Instruments can gather spectra, fields, dust measurements, and images during the approach. Autonomous software can choose exposures long before Earth sees the result. A flyby is also simpler because the probe need not carry braking hardware. Breakthrough Starshot uses that bargain. It trades a long stay for a payload light enough to accelerate. The trade shapes the science plan years before launch. Instruments cannot circle back to inspect a cloud twice. They must observe the system in a sequence arranged around one line through 3 moving stars. Approach images can update that sequence. If a planet appears slightly away from its predicted position, the craft may adjust its camera timing even when its trajectory cannot change much. Software turns the final weeks into a moving appointment book. Several probes arriving along different lines can stretch the encounter. One may pass Proxima first, while another reaches the bright pair months later. The combined mission gains time by distributing it among separate travelers. An orbiter cannot make the same trade. It must remove almost all its incoming velocity. The energy that created the motion has to go somewhere. A conventional rocket points its engine forward and burns fuel. The exhaust carries momentum ahead while the craft slows. For an interstellar vehicle, the braking fuel had to be accelerated from home, which makes the departure mass rise sharply. A second laser array at Alpha Centauri could push against the sail from the other side. There is, rather inconveniently, no laser array waiting there. Building one would require arriving first. Starlight can push a sail, but ordinary stellar pressure is far weaker than the launch beam. A very large sail could begin slowing years before arrival. The design would need to survive deployment and aim precisely around a moving triple system. Magnetic sails offer another possibility. A superconducting loop can create a broad magnetic field. Charged particles in the interstellar medium and stellar wind would be deflected, giving the craft a slow braking force. The idea carries no traditional propellant. It carries a large loop, cooling demands, power electronics, and uncertainties about the plasma ahead. Its sail works better at some speeds than others. Ordinary drag on a Starshot wafer is far too small to stop it usefully. One analysis found that gas drag would barely change the cruise time. The same thin medium that damages the surface does not provide a convenient brake. A magnetic sail tries to interact with far more plasma than the vehicle's physical area would meet. Its field reaches outward and bends charged particles before they touch the craft. Momentum passes through electromagnetism rather than a solid parachute. Near Proxima, the stellar wind may strengthen the available braking force. It also varies with the star's activity. A system designed around an average wind must remain useful when the red dwarf chooses a different afternoon. One study combined magnetic and electric sails for a heavier craft, arriving at 5% of light speed. Under its assumptions, braking to interplanetary speed took nearly 3 decades. That is a model result, not a timetable. The number shows the shape of the problem. Deceleration can last as long as the cruise. A voyage advertised as a century may spend a large part of that century simply becoming slow enough to look around. Braking can begin before the stars look large. Weak forces become useful when they work across years. Navigation then has to balance patience with precision, because every early adjustment changes the geometry of the final encounter. Arrival is prepared in the dark, while the destination still resembles an ordinary point of light. Gravity can bend a path near a star, but gravity alone does not erase speed. A carefully chosen flyby can exchange energy within a multiple star system. The craft must still arrive on exactly the right line and survive the close pass. Atmospheric braking works at planets inside the solar system. It turns motion into heat in air. An interstellar craft cannot assume a suitable atmosphere, and arriving at a fraction of light speed would make any such attempt destructive. The mission can choose a lower cruise speed from the start. That reduces shielding and braking demands. It adds years or centuries, which increases reliability and life support demands. Every design chooses where to place the difficulty. Fast flight burdens energy, impacts, and stopping. Slow flight burdens time, maintenance, and generations. Robotic scouts can accept a quick pass. They can send a burst of observations and continue into the galaxy. A later mission may use those measurements to choose a world worth slowing for. This creates a gentle ladder. Telescopes study the system from Earth. Fast flyby probes provide close images. Slower, heavier craft may eventually arrive with the ability to brake. No rung needs to pretend it is the last. The first images from another star would not make a human voyage easy. They would make the destination less imaginary. Data must still cross homeward. The signal begins its 4-year return after the probe has already left the system behind. By the time the first complete image reaches Earth, the craft may be another light year farther on. Mission Control cannot ask for a retake. The photographer is gone. That gives every exposure a quiet seriousness, though the camera itself will feel no nerves. Stopping changes the meaning of arrival. Flybys prove the crossing. A rendezvous creates time for maps, repeated measurements, and perhaps a small orbit around a new sun. For people, stopping is not optional. A crew cannot spend 40 years traveling only to watch the destination pass in minutes. The habitat must become part of the new system or continue forever. That requirement makes the crewed problem much larger than a fast sail. It needs a vehicle built not merely to cross space, but to remain a functioning place, while speed gathers and then falls away. The second half of the trip, therefore, begins inside the first drawing. Every tank, sail, loop, and radiator must know how the craft will slow. Only a vehicle that can stay turns its destination real. Crewed starships cannot be only vehicles. For decades or centuries, they must perform the ordinary work of a world. They need air, water, food, power, warmth, waste processing, medicine, and repairs. Earth provides those services so completely that they disappear into the background. Rain moves water. Plants renew oxygen. Soil and microbes return nutrients. The atmosphere carries heat away and presses gently on every room. A ship must replace each service with machinery or a living cycle. It must also fit the replacement inside a hull. The planet has not been notably helpful about sharing its operating manual. Water is the clearest success so far. The International Space Station has demonstrated recovery of about 98% of its water. Moisture from breath, sweat, and urine can become drinking water again. That is a splendid piece of engineering. It is not a perfectly closed loop. Filters wear out, pumps fail, small losses continue, and replacement parts arrive from Earth. Over 40 years, a 2% unrecovered fraction cannot simply vanish on every pass through the system. The ship needs higher effective closure, stored reserves, repairable hardware, and ways to recover water from every useful stream. Air has similar layers. Carbon dioxide must be removed before it accumulates. Oxygen can be produced by splitting water. Some systems combine carbon dioxide and hydrogen to recover part of the water and oxygen cycle. The station still depends on logistics from the ground. A Starship cannot. Its air system must survive many equipment generations without a warehouse beneath it. Food is harder because food is both material and ecology. Stored meals cover months or years. Decades call for farms, seeds, light, nutrient loops, pollination, disease control, and a stable community of microbes. Carbon is only one traveler in that loop. Nitrogen, phosphorus, potassium, and trace minerals must return from waste to roots in forms plants can use. Microbes perform much of that quiet chemistry. A healthy farm is therefore a partnership among leaves, lamps, water, and organisms too small to appear on a crew list. Crop diversity protects both nutrition and harvests. One disease should not threaten every meal. Seeds, tissue cultures, and carefully stored genetic material provide ways to begin again. Their storage rooms would be humble versions of forests, waiting in labeled drawers. Meanwhile, growers would keep living varieties changing under lamps, season after invented season. A harvest calendar becomes another onboard clock. Plants do grow in orbit. NASA's small station garden has raised leafy crops and flowers in a chamber about the size of carry-on luggage. It is research, not a farm for a city. A complete diet needs more than lettuce. Protein, fats, minerals, and variety matter. Crops also create stems, roots, and waste that must return to the nutrient cycle without carrying disease. Artificial light for agriculture consumes power and produces heat. Windows admit starlight poorly between stars, and large, transparent surfaces complicate shielding. The garden may glow under lamps deep inside the ship. Life support needs redundancy. Two identical pumps can share spare parts, but one hidden flaw may disable both. Using different pump designs reduces that risk and doubles the training manual. The same choice appears everywhere. Common hardware is easier to maintain. Diverse hardware is less likely to fail in the same way. A starship becomes a long negotiation between simplicity and resilience. Spare parts cannot cover every future fault. A machine shop must make replacements. That means carrying tools, raw material, design files, measuring equipment, and people who understand why an old valve was shaped oddly. modern additive manufacturing can form useful parts in orbit. It cannot yet produce every bearing, computer chip, seal, sensor, or medicine from basic feedstock. The industrial chain behind one small pump may involve factories spread across continents. A self-repairing ship must compress part of that chain. It needs the ability to recycle metals and polymers, test new pieces, and preserve knowledge. Manuals alone are not enough if the measuring tools drift out of calibration. Power must continue through the dark. Solar panels weaken quickly after departure because the sun becomes a bright star. A long mission may rely on nuclear fission, fusion if it becomes practical, or energy beamed from afar during only the early stage. Every power source creates waste heat. Radiators must release it without air. A warm town inside a cold vacuum still needs a large surface devoted to cooling. The ship also needs shielding, which can help with temperature and radiation. Water stores may line inhabited rooms. Food and equipment can add mass around sleeping quarters, allowing supplies to perform two jobs. Gravity presents another decision. Long exposure to weightlessness changes bones, muscles, fluids, vision, and balance. The most direct artificial gravity comes from rotation. Spin a habitat, and its floor presses outward beneath the crew. A wide ring can turn slowly and still provide useful gravity. Narrow rings must rotate faster, which can make head movements feel strange. The rotating section needs bearings, or a whole vehicle designed to spin. Pipes, cables, docks, and radiators must work with that motion. A simple circle on paper becomes another patient stack of details. Living systems add surprises because they evolve. Microbes reproduce quickly. Plants respond to light and gravity. Human communities alter habits, diets, and expectations. The ship cannot freeze its culture or biology at launch. It must stay stable while allowing change. That is a different requirement from keeping a probe exactly as built. No closed habitat has supported a human community for generations without outside material and expertise. The station provides months of experience. Submarines provide long confinement. Polar bases provide isolation. None is a starship. The gap between those examples and interstellar self-sufficiency is wide, but it contains useful steps. Better water recovery helps lunar bases. Improved food cycles help Mars missions. More repairable machines help every remote outpost. A crude Alpha Centauri craft would gather all those lessons into one place. Its decks might hold farms, workshops, clinics, archives, and rooms where nothing especially scientific happens. People would eat breakfast, mend clothing, settle small arguments, and complain about ventilation. Those ordinary moments would show that the extraordinary machine still worked. Its habitat would carry no blue sky unless someone painted one. Yet it would carry the functions that make a sky possible to live beneath. Air would circulate, water would return, green leaves would open under lamps. That is what turns a starship into a world. It does not imitate Earth's appearance. Instead, it keeps enough of Earth's cycles going that a small, warm community can remain alive between one sun and the next. The human body is not cargo. It breathes, repairs itself, changes with age, and expects a gravity field. Any crude design must treat biology as part of the vehicle. NASA groups the main hazards of long spaceflight into 5 families. They are radiation, isolation and confinement, distance from Earth, altered gravity, and a closed or hostile environment. An interstellar voyage combines all 5 for longer than any experiment. Gravity becomes noticeable first. On Earth, bones carry weight all day without receiving a meeting invitation. Muscles work against the floor. The heart pumps upward through a body shaped by a steady downward pull. Remove that pull, and the body adapts. Weight-bearing bones can lose roughly 1 to 1.5% of mineral density per month during spaceflight on average. Exercise and diet reduce the losses, and astronauts vary. That rate must not be extended as a straight line for 40 years. Bodies do not behave like bank accounts. Countermeasures, plateaus, individual differences, and future treatments all matter. The lesson is simpler. Long weightlessness is not neutral. A crew that plans to walk after arrival needs useful gravity during the crossing, or a much better substitute. Station astronauts exercise for hours each day. Treadmills use straps to pull them toward the belt. Resistance machines imitate weight without iron plates falling around the cabin. The routine works well enough for missions measured in months. It also consumes crew time and equipment. A broken exercise system aboard a Starship becomes a medical issue, not an inconvenience. Rotation offers a fuller answer. A spinning ring presses feet toward its outer wall. The motion can create an effective downward direction without inventing new physics. Radius matters. A larger ring turns more slowly for the same apparent gravity. Slow rotation reduces dizziness, and the strange sideways effects felt when someone moves a head or raises an arm. Large rings add structure and mass. They need balance. A load of water moved from one side to another can make the habitat wobble unless control systems respond. Designers might spin 2 sections in opposite directions. That cancels some angular momentum and gives the ship a calmer attitude. It also doubles the number of large moving structures asking for maintenance. Radiation is less easily imitated away. Earth's magnetic field and atmosphere block or soften much of what arrives from space. Beyond the magnetosphere, crews meet solar particles and galactic cosmic rays more directly. Solar storms can produce intense bursts. A ship needs a sheltered room surrounded by water, food, or other shielding. The crew could wait there while instruments track the event. Galactic cosmic rays arrive from many directions and carry high energy. Thick shielding helps, but some materials create showers of secondary particles when struck. More mass is not automatically better in every arrangement. Hydrogen-rich materials are useful because their light nuclei can slow charged particles with fewer heavy fragments. Water and polyethylene appear often in shielding studies. A habitat may place tanks around its busiest rooms. At interstellar speed, the gas ahead becomes an additional radiation source. The front shield protects machinery and living space together. A crewed craft may need long, narrow geometry with most occupied volume behind a deep bow. Medicine also changes with distance. There is no evacuation. A doctor cannot send a patient home, and a specialist on Earth cannot guide a procedure in real time after the first few light months. The crew needs broad medical training, diagnostic tools, medicines with long shelf lives, and equipment that can make replacements. Dentistry becomes part of astronautics. A tooth has impeccable timing when no clinic is nearby. Future clinics would need calm routines for problems that cannot be handed back to Earth. Pharmaceuticals can degrade under radiation and age. Some may be manufactured aboard. That requires chemical feedstocks, quality control, and knowledge that survives changes in staff. The mind has its own environment. Isolation studies and long missions show that privacy, meaningful work, sleep, team selection, and conflict management matter. A crew cannot spend decades in permanent emergency mode. Light becomes part of the habitat's clock. Bright mornings and dim evenings can maintain a shared daily rhythm even when no natural dawn reaches the hull. Individual cabins also need darkness, quiet, and control. A schedule imposed by machinery still works better when it leaves room for someone to close a door. Medical records must travel as carefully as people. Long trends reveal changes that one examination might miss. Private data needs protection, while emergency information must remain available after staff and computer systems change. The clinic is both a room and a promise that future caregivers can understand the past. Its instruments also need calibration standards, sterile supplies, and repairs that remain possible far from a factory. Ordinary time needs texture. Meals, celebrations, gardens, projects, music, and quiet rooms help days differ from one another. The ship may create artificial seasons through light and temperature, even while the stars outside barely shift. Windows offer comfort and add shielding problems. Cameras and displays can provide views without opening a large, transparent weakness in the hull. Some rooms may show the departing sun as a shrinking point, then replace it with a garden wall. Communication with Earth fades from conversation into correspondence. Early messages may return within hours or days. Later, replies take years. The crew must solve most personal and operational problems locally. That autonomy can be protective. No distant office can hover over every decision. The people aboard become the trusted experts on their own small world. Isolation does not guarantee collapse. Human groups have lived in remote stations, submarines, and spacecraft with skill and kindness. Interstellar duration simply removes the assumption that patience alone will cover poor design. Space must exist for disagreement. Governance must be clear. Work must remain useful after the excitement of launch becomes family history. None of these hazards belongs to anyone alive tonight. No crewed Alpha Centauri mission is waiting on a launch pad. They are design questions held at a safe distance, studied so future choices can be wiser. The body is also resilient. Bone rebuilds, muscles train, minds make homes in unlikely places. Medicine advances because limits are measured rather than ignored. A well-designed ship would not ask people to endure 40 years of injury. It would carry gravity, shielding, gardens, privacy, and time for ordinary life. The crossing would need to be lived, not merely survived. Somewhere inside the rotating habitat, feet would meet a floor. Water would move through pipes. A lamp would rise over leaves on a schedule, creating morning where no sunrise could reach. If a crossing lasts longer than one working life, the ship changes category. It becomes a generation ship. Some people aboard will be born after departure, and others will die before arrival. At 1% of light speed, Proxima is more than 4 centuries away. That allows many generations. At Voyager's rate, the voyage reaches into thousands of them, which is not a practical human plan. Faster designs shorten the question without removing it. A 42-year cruise covering a light year each decade could begin with adults and end with their grown children. Acceleration and braking would add time. The first generation chooses to leave. Its successors do not. Children inherit a ship, a destination, and a promise made before they existed. That is not only an engineering issue, it is an ethical one. A mission cannot treat future people as spare parts for a plan. They need education, health, freedom, and a real voice in governance. Future residents may decide that the original destination is unsafe, or that the ship should follow a different path. A design that cannot permit judgment has confused obedience with reliability. Population size receives much attention because genetic diversity matters. In 2018, one Monte Carlo study modeled a 6,300-year voyage toward Proxima b. Under its specific reproductive rules, 98 initial people produced a successful result in all the modeled runs. That number is not a universal ticket price. The study used controlled assumptions about pairing, births, accidents, and health. It did not prove that 98 people can support every skill, institution, and surprise for 6 millennia. Later modeling added more genetics and radiation effects. Larger starting populations gave more resilience. Hundreds may be more realistic under some scenarios, while frozen reproductive cells could preserve additional diversity. A genetic archive adds freezers, power, records, medical procedures, and consent. It can broaden options. Still, it does not turn a small crew into a complete society by magic. Skills need diversity too. A ship requires clinicians, engineers, growers, teachers, programmers, machinists, cooks, mediators, and people who can learn several jobs. One specialist in each field is a single point of failure wearing shoes. Education must reproduce expertise, not merely information. A manual can describe surgery. It cannot replace years of supervised practice. Each generation needs teachers and enough real work to train the next. Archives need several forms because no storage medium is immortal. Printed diagrams survive different failures than electronic files. Multiple copies can live in separate parts of the ship, protected from one leak or fire. Periodic copying also reveals corrupted records before the last readable version disappears. That matters. Simulations can preserve rare skills between real emergencies. Crews may rehearse surgery, crop failure, navigation faults, and pressure loss inside safe models. Practice keeps old knowledge connected to living hands. The calmest emergency is the one that has already been visited in training. Its lessons can pass forward without requiring a real disaster. The same applies to machine repair. A child may apprentice beside someone who learned from an engineer born on Earth. Decades later, the apprentice becomes the keeper of a pump design older than anyone alive. Culture will change. Language shifts in a few generations. Traditions gather new meanings. A launch day ceremony may become a holiday whose original weather nobody remembers. Earth would remain present through recordings and messages. It might also become abstract, like a place from ancient literature. Children tend to treat assigned history with a healthy amount of yawning, even when the history contains an entire planet. The destination changes from a promise into a curriculum. Proxima becomes a red star in lessons, then a brighter point through instruments, then eventually a source of warmth and radiation that shapes daily planning. The mission needs a reason that can survive revision. Our founders wanted this, is too thin. A living society may continue because the ship is its home and safe arrival expands its choices. Governance could begin with a constitution written before launch. It would need methods for amendment, courts or councils, emergency powers, and limits on those powers. Every word would be tested by circumstances the authors could not predict. The vessel must also permit dissent. People may disagree about births, resource use, risk, work, or whether to approach a planet. Suppressing every disagreement stores pressure inside the habitat. Small communities can become intimate and supportive. They can also make privacy rare. Architecture matters. Doors, quiet rooms, separate neighborhoods, and places with no official purpose can protect social life. Birth and childhood change the medical plan. Pregnancy has never been carried from conception to birth in human spaceflight. Partial gravity, radiation protection, and developmental health remain large unknowns. A prudent generation ship would provide near-Earth gravity in family areas. It would shield children more carefully and keep medical research under strict ethical rules. No mission goal excuses treating a generation as an experiment without consent. There is another odd problem called the weighting calculation. Technology may improve while the first ship travels. A faster craft launched later could overtake it and arrive first. This does not mean every mission should wait forever. It means departure timing is a choice. A society may send probes early, learn from them, and delay people until propulsion improves enough to reduce inherited years. Robotic exploration is especially valuable here. It can confirm whether a destination has stable orbits, dangerous radiation, useful materials, or any planet worth approaching. A generation ship should not spend centuries sailing toward a guess that a telescope could refine. The ship itself may become more important than the target. After several generations, it is a settlement already functioning in space. Arrival offers a new sun and resources, but success began long before. That thought softens the old picture of people trapped in a corridor. A true world ship would contain towns, farms, workshops, schools, and room for change. It would travel, but daily life would not feel like waiting at a gate. The founders would become portraits. Their names might survive on runes or gardens. A more useful gift than a command to continue would be a vessel capable of supporting choices they never imagined. Near the end, the destination would brighten year by year. The people making arrival decisions would belong to the ship, not to the century that launched it. That is exactly why the decisions should be theirs. The stars do not demand a generation ship. It is one possible answer to a slow crossing. Before choosing it, an advanced society may find a stranger kindness inside relativity, where speed changes the rate at which clocks gather years. Time does not pass at one universal rate for every observer. Motion changes how clocks compare. This is one of special relativity's measured facts, not a decorative idea added to starships. The speed of light in vacuum is the same for every freely moving observer. Space and time adjust around that rule. A moving clock is measured to tick more slowly than one at rest in the chosen frame. Particle accelerators see the effect. Fast, unstable particles survive longer in the laboratory than they would at rest. Navigation systems also account for relativity to keep clocks aligned. The change is tiny at ordinary speeds. Cars, aircraft, and planets still experience it, but daily life hides the difference. Near light speed, the effect becomes large. At a tenth of the cosmic speed limit, time dilation is modest. A coast to Proxima, lasting about 42.5 years in Earth's frame, would feel only a few months shorter aboard, before acceleration and braking are included. That surprises people who expect any fraction of light speed to unlock dramatic time travel. 10% is extraordinary engineering and still gentle relativity. The clock has only begun to soften. At 1/5, the Earth frame coast lasts a little over 21 years. The craft's clock records roughly 5 months less. A Starshot probe has no opinion about the saving. At 90% of light speed, the contrast becomes clear. Earth measures about 4 years and 9 months for the crossing. A clock coasting with the craft records a little over 2 years. At 99%, Earth still measures slightly more than 4 years, because Alpha Centauri is more than 4 light years away. Around 7 months pass for the traveler during the coast. The comparison is governed by a quantity called the Lorentz factor. At low speed, it remains close to 1. As velocity approaches light, the factor grows, and the difference between Earth time and ship time grows with it. Length changes in the traveler's description as well. The distance ahead is contracted. Alpha Centauri is not physically dragged closer, yet the moving frame assigns a shorter separation between departure and arrival. Those are two views of the same geometry. Earth says the moving clock gathered fewer months. The traveler says the road between the stars was shorter. Both calculate the same reunion events. Those examples ignore the time and distance needed to accelerate and slow. They also ignore the energy bill. Relativity shortens the traveler's experience time only after the vehicle reaches a speed that is immensely difficult to produce. Nothing with mass can reach light speed through finite acceleration. As speed rises, each added fraction requires more energy. The last small gap toward light becomes increasingly expensive and never closes. No rule forbids coming very close. The exact limit remains unreachable. In theory, a powerful enough engine could push a craft to 90 or 99%, provided energy, heat, shielding, and impacts were solved. Those provisions carry most of the difficulty. At such speeds, dust and gas strike harder. The forward radiation environment worsens. Braking demands nearly as much care as acceleration. Relativity is sometimes described as a loophole for crossing the galaxy in one lifetime. From the traveler's perspective, enough speed can compress experienced years dramatically. Earth and the galaxy do not share that shorter calendar. A traveler returning from a long relativistic voyage would have aged less than people who stayed. The effect is often told through twins. One leaves, turns around, and returns younger than the other. There is no paradox once their paths through space-time are compared. The traveling twin changes frames during departure and return. Those two world lines simply contain different amounts of proper time. For Alpha Centauri, the difference need not become tragic. The system is close enough that even Earth measures only a few years at near light speed. Its harder loss lies in the impossible engine, not generations passing at home. Acceleration can also create apparent gravity. A ship that accelerated at roughly Earth gravity would give its crew a familiar floor. Halfway there, it could turn and use the same acceleration to slow. On paper, such a profile reaches Alpha Centauri within a handful of years for both Earth and crew. The engine would need to deliver enormous thrust continuously while carrying its energy source and reaction mass. No known drive can do that for a large craft. The calculation describes what relativity permits, not what engineering provides. It is a clean window onto the difference between possible and available. Time dilation does not let a message beat light. A radio pulse from Proxima still takes about 4¼ years in Earth's frame. The crew's clock cannot make the receiver obtain it sooner, nor does the moving crew feel its own time running slowly. Heartbeats, thoughts, and meals remain normal aboard. The difference appears only when clocks following different paths are compared. That makes relativity oddly gentle from inside the ship. Nobody watches a slow second hand. A cabin day keeps its usual length while distance contracts in the traveler's frame. Meanwhile, the stars ahead seem altered by motion. Their light shifts toward shorter wavelengths. Stars behind redden. The cosmic background brightens in the forward direction, adding to the engineering challenge. Starlight also crowds toward the forward view through relativistic aberration. At extreme speed, much of the sky appears gathered ahead. Navigation cameras would need to compare that distorted dome with carefully transformed maps. Light from the front carries more energy in the ship's frame. Visible radiation can shift toward ultraviolet, while the faint microwave background moves upward as speed rises. Shielding becomes an optical and thermal problem, as well as a particle problem. None of this would feel like the cabin rushing through a tunnel. Motion at constant velocity has no local sensation. A sealed laboratory cannot measure an absolute speed without looking outside. At lower speeds, those effects are mild. A crew moving around 108 million kilometers each hour would still see a recognizable sky, with careful instruments correcting small shifts. Their main calendar remains long and ordinary. Relativity therefore offers no cheap escape from Alpha Centauri's distance. It offers a truthful exchange. Spend extraordinary energy on speed, and the people aboard may experience less time. The exchange is beautiful because it is real. It has been measured in clocks and particles, yet the universe has attached the receipt to the engine. For now, human time follows the slower plans. Probes take years, light takes 4. A crude ship remains a drawing, and every clock on Earth is free to tick at its familiar pace. Communication is the one part of interstellar travel that humanity already knows how to begin. Radio waves and laser light move at the cosmic limit. They need no road, only a transmitter, a receiver, and time. From Earth to Proxima, the minimum delay is about 4 years and 3 months. A message sent on a child's first day of school might arrive near the end of the 4th year. The answer would return when the child was several grades older. That makes a complete question and reply roughly 8 years and 6 months long. The number assumes both sides answer immediately. Machines rarely show such social efficiency. A crew could send regular reports without waiting. Earth could do the same. The result would be 2 streams of letters crossing in opposite directions, each one written without knowledge of the latest mail from the other side. This is not a conversation in the usual sense. It is correspondence. People once sustained friendships and scientific debates through letters that took months. Interstellar mail simply gives the habit a larger calendar. Delay changes mission control first. Engineers on Earth cannot guide a landing or repair as it happens. By the time a description arrives, the crew or probe has already acted years earlier. The vehicle must diagnose faults locally. It needs stored procedures, simulation tools, and enough intelligence to adapt when the fault is not in any manual. Earth becomes an archive and advisor, not a hand on the controls. Eventually, the distant reply may become history. Signal strength creates another problem. Light spreads as it travels. A beam that begins narrow grows wider, and a receiver catches only a small part of its energy. Radio transmitters can use large antennas and high power. Laser communication concentrates energy into a narrower beam, but pointing becomes more demanding. A tiny error can place Earth outside the beam entirely. Voyager illustrates the gentle version of this challenge. Its transmitter uses power comparable to a household light. By the time the radio reaches Earth, the signal is extraordinarily faint. The Deep Space Network gathers that whisper with large dishes. Receivers cool their electronics, filter noise, and integrate the signal over time. Careful listening creates usable data from very few arriving photons. Alpha Centauri multiplies the range by thousands. A Starshot-scale probe has far less room for a transmitter or power source. The proposed sail may double as part of an optical system, focusing short laser bursts toward home. Energy can accumulate slowly in a capacitor, then leave in a brief pulse. The receiver knows when and where to look. Several probes may relay or combine their reports. Data must be chosen before transmission. Raw images are large. The craft can compress them, discard damaged frames, and rank observations by scientific value. That gives software an editorial job in another star system. It must decide which narrow strip of atmosphere, which magnetic reading, or which view of a planet deserves the first precious bits home. Compression should preserve surprises. An algorithm trained only to expect familiar worlds might erase the feature nobody predicted. Mission software needs ways to keep anomalies without filling memory with noise. The probe can send summaries first and details later. A simple health code might arrive before an image. Then a small preview appears, followed across months by higher quality data. Every packet needs error correction. Interstellar noise, pointing drift, and hardware damage can alter bits. Redundant patterns let receivers reconstruct missing pieces, much as a torn sentence can still be understood from its neighbors. Clocks matter too. The craft must know when each measurement occurred and where it was. Its onboard time will differ slightly through motion and gravity, so navigation software applies relativistic corrections. For a human settlement, communication becomes social as well as technical. News from Earth is already 4 years old on arrival. Elections, births, discoveries, and weather have all moved on. Messages from the ship reach people who did not share the moment described. One celebration arrives after its candles are gone. A difficult year may be finished before anyone at home learns it began. That delay can sound lonely if held too long. It also removes urgency. No one is expected to reply at once. A message can be careful, complete, and addressed to a future reader. Families might exchange long recordings. Children aboard could meet grandparents through archives and delayed replies. The relationship would be real, though it would never occupy the same present. Earth itself would change between exchanges. New languages, customs, and technologies could appear during a slow voyage. Translation tools and shared archives would keep the two communities legible to each other. The ship might preserve old communication standards for compatibility. Earth would need receivers able to understand them decades later. A file format becomes a promise across generations. There is no guarantee that every promise survives. Antennas may fail. Institutions may close. A resilient mission would publish its protocols widely, so no single organization owns the ability to listen. The sky offers a useful anchor. From Alpha Centauri, the sun would be one star among many, though its position is predictable. A transmitter can use nearby stars to orient itself and place its beam toward the small moving target around the sun. Earth will not sit where the probe last saw it. Light time calculations include the planet's orbit, the sun's motion, and the receiver's future location. The beam is addressed to an appointment 4 years ahead. If the pointing works, The signal arrives without ceremony. A detector records a faint pattern. Computers test it, correct it, and discover that a machine launched decades earlier has spoken from another sun. The first message may contain very little, a health flag, then a star position. Finally, a compressed line showing that the camera opened. Even one verified packet would prove that information crossed the whole Gulf twice, once as a spacecraft and once as light. Later packets could take years to decode fully. Scientists would compare them with telescope observations made during the probe's flight. The old and new views would sit side by side, separated by 4 light years and a generation of instruments. Communication cannot carry food, people, or spare parts. It carries knowledge. That is enough to make a remote place part of a shared scientific world. The two systems would never share a signal now. They could still share a record. Signals would pass each other in the dark. One stream telling Earth what the probe found, the other carrying updated maps toward a traveler already far beyond the place they describe. At the other end of the crossing, the nearest confirmed planet is Proxima Centauri b. Astronomers announced it in 2016 after measuring a tiny repeated motion in its star. The planet itself was not photographed. Gravity supplied the clue. As the planet circles, it pulls Proxima slightly toward and away from Earth. That motion shifts features in the star's spectrum by a minute amount. The method gives a minimum mass because the orbit's tilt is not fully known. Current measurements place that minimum close to Earth's mass, about 1.05 times as much. Proxima b completes an orbit in roughly 11 days. It travels only about 7 million kilometers from its star, far closer than Mercury lies to the Sun. That orbit sounds hot until the star is considered. Proxima is small and faint. Its habitable zone sits close in, and Planet B receives an amount of starlight that allows liquid water in some models. The phrase habitable zone is easy to overread. In astronomy, it describes a range of possible heating. It does not announce oceans, air, plants, or inhabitants. Liquid surface water also needs suitable pressure and an atmosphere. No telescope has yet established whether Proxima b possesses one. The planet does not cross directly in front of the star from Earth's viewpoint, which removes the easiest atmospheric measurement. Proxima is magnetically active. It produces frequent flares with ultraviolet and X-ray radiation. Strong events may erode a planet's atmosphere, especially if the world lacks a protective magnetic field. May is important there. Models disagree because the starting atmosphere, magnetic field, chemistry, and history are unknown. Some atmospheres could be lost. Others might persist or be replenished. The planet may be tidally locked, with one face tending toward the star. Close orbits often produce that state. The exact rotation has not been measured, and other spin patterns remain possible. Even a locked world is not automatically frozen on one side and scorched on the other. A thick enough atmosphere or ocean can move heat. Climate simulations produce many outcomes because the missing inputs matter. That is the honest texture of Proxima b. It is not a second Earth and not a confirmed wasteland. Instead, it is a nearby, roughly Earth-mass planet, receiving interesting warmth from a difficult star. Closer to Proxima lies planet D. Its year lasts about 5 days. The minimum mass is only around a quarter of Earth's, making it one of the lightest worlds found by radial velocity. With that small mass, the planet orbits closer than the habitable zone's usual inner edge and receives much stronger stellar energy. It is likely too warm for familiar surface water. Its main value may be what it teaches about very small planets around red dwarfs. The signal for Proxima D was first tentative. New infrared measurements published in 2025 confirmed it more securely and refined both known worlds. Careful repetition turned a candidate into a planet. Proxima C has moved the other way. A long-period signal once suggested a more distant planet. Current evidence remains inconclusive, and the NASA Exoplanet Archive treats it as a candidate rather than confirmed. That change is not a failed discovery. It is the catalog doing its job. A name can stay in the notes while the count waits for stronger evidence. The bright pair, Alpha Centauri A and B, has no confirmed planet as of this research pass. Yet Alpha Centauri A now holds the most intriguing candidate in the system. James Webb used its mid-infrared instrument to search close to the star. A coronagraph blocked much of Alpha Centauri A's glare, while careful processing removed patterns from both bright stars. In August of 2024, the team found a faint source more than 10,000 times dimmer than Alpha Centauri A. It appeared at roughly twice the Earth-Sun distance from the star. The source did not appear in follow-up observations during February and April of 2025. That might sound like a disappearance. Orbital models show that a planet on many allowed paths would have moved too close to the star's glare to be seen at those times. Background galaxies, asteroids, and instrumental artifacts were tested. The team concluded that a planet is a strong explanation, not a confirmed one. One convincing sighting remains one sighting. If the source is a planet, models suggest a cool gas giant around the mass of Saturn. Its orbit may range between about 1 and 2 times Earth's distance from the Sun and last 2 or 3 years. That would place it within the broad habitable zone of a Sun-like star. The planet itself would not offer a solid surface or familiar life. Large moons, if any exist, are presently pure speculation. The expected orbit may bring the candidate into view again later in 2026. If it reappears near the predicted location, the case would strengthen. Continued absence would narrow or challenge it. This makes the result especially alive tonight. The object sits in the careful middle ground between discovery and correction. It has earned another observation, not a triumphant nameplate. A probe would change the available questions. From nearby, it could separate the stars cleanly, map dust, and search a wider range of planet sizes. It might measure atmospheres without fighting the same glare geometry seen from Earth. A fast flyby would still face limits. Proxima, Alpha A and Alpha B occupy a large system. One trajectory cannot pass close to every possible world. Mission planners must choose which member receives the brief encounter. Proxima B is the nearest known rocky target and circles an active red dwarf. Alpha Centauri A offers a sun-like star and a candidate giant. The central pair may reward a different path than the outer companion. Early close data may remove romance from some ideas. Proxima B could be bare. The web source could prove to be something other than a planet. Other worlds may appear where none were expected. Any result is useful. An empty orbit constrains planet formation. Thin atmospheres test flare models. A cold giant beside a solar twin offers the nearest laboratory for comparing another mature planetary system with this one. That may sound less dramatic than a new Earth waiting next door. It is also much more interesting. The real Alpha Centauri system is still being written by observations, one cautious line at a time. Nothing there knows that it has become a destination. Meanwhile, the stars burn. The confirmed worlds pull gently on Proxima, and one faint candidate waits for another look from a telescope 4 light-years away. The first crossing begins before anything leaves for Alpha Centauri. It begins with telescopes learning what deserves a visit. Every better orbit and atmosphere measurement removes risk from a mission that cannot turn around. Ground observatories will keep measuring the small wobble of Proxima. James Webb and later instruments can return to Alpha Centauri A. New coronagraphs may separate fainter planets from the bright pair. The candidate giant offers a near test. Its predicted motion can be checked within years, not centuries. A successful confirmation would refine the system map before any sail is built. Closer to home, interstellar precursor probes can travel hundreds or thousands of astronomical units. They do not reach another star. Instead, they test power, communication, autonomy, and the medium through which a later craft must pass. Voyager was not designed as such a precursor, yet it already measures the space outside the heliosphere. Its old instruments give the first direct sample of the environment beyond the solar wind. Future probes can leave faster and carry modern sensors. They may map dust and magnetic fields along the general Alpha Centauri direction. Meanwhile, their electronics can test whether decades of travel remain possible without resupply. Laser sail work can advance in smaller steps. Laboratory materials can survive brighter beams. Phased arrays can hold focus. Tiny spacecraft can demonstrate pointing, folding, and optical communication within the solar system. No single test needs to promise another star. One sail that reaches the outer planets quickly would already be useful. A laser link that returns data from deep space would already improve exploration. This matters because ambitious programs survive better when each step produces value. The final objective may be distant, while the technologies help astronomy, planetary defense, power transmission, and remote science on the way. Materials science has a clear list. Sails need extreme reflectivity with very low mass. Shields need resistance to erosion. Electronics need radiation tolerance, and the ability to sleep for years without forgetting how to wake. Autonomy has another list. A probe must navigate, detect faults, schedule observations, and decide what to transmit. Its software should remain understandable enough for engineers to trust before launch, and scientists to interpret after arrival. Power storage must work through long darkness. Small radioisotope sources may keep clocks and memory alive. The arrival sequence can save energy for years, then spend it during one crowded hour. Communication needs receivers as much as transmitters. Large optical arrays on Earth or in space can search for the probe's faint beam. Open protocols ensure that future observatories still know how to listen. The launch beam presents civic questions too. A powerful laser requires safety, international coordination, and careful control of airspace and satellites. Engineering cannot declare those matters somebody else's department. The first mission may launch many craft over several nights. Their paths spread slightly. Some fail early. Others report healthy sails, quiet electronics, and a dark route ahead. For years, their signals grow slower and fainter. The sun becomes a navigation star behind them. Dust counters record occasional taps, too small for any ear. The probes would cross the heliopause within days or weeks, at relativistic speed. Voyager needed decades. That contrast would mark the moment the experiment became genuinely interstellar. Then, the long coast begins. Mission teams change. Students who watched launch become the engineers receiving approach data. Archives pass from one software generation to another. 20 years is long for a project and short for a star. Institutions have operated observatories and missions across similar spans. The challenge is difficult, without requiring an unknown civilization to remain unchanged for millennia. As Alpha Centauri grows in the instruments, the probes prepare themselves. Cameras warm, star trackers update, stored target lists yield to current observations. Some may aim at Proxima, others may favor Alpha Centauri A and B. The swarm turns one impossible appointment into many small chances. Across the wider system, each encounter lasts minutes to hours. Images enter memory, spectra form. Instruments feel magnetic fields that have never touched a human-made sensor. There is no applause aboard. The craft performs its sequence and points home. A laser begins sending the smallest useful version of what happened. 4 years later, a receiver on or near Earth finds the pattern. Checksums match. A first close view of another stellar system enters a room whose designers may not have been born at launch. That event will not mean people can follow. A gram-scale flyby and a crude rendezvous remain vastly different. The honest ladder keeps its rungs separate. Robotic success can guide a slower craft able to brake. Better propulsion may come from fusion, beamed sails, magnetic systems, or an approach not mature enough to name. No schedule can be promised. The night began with 4.25, a number small enough to fit beside a star's name. It unfolded into a ruler stretching from a classroom to another city. Voyager crossed that model, one patient fraction at a time. An old equation weighed the fuel. Paper ships pulsed with nuclear fire and fusion pellets. A mirror sail caught a laser, folded itself narrow, and met the fine dust between suns. The imagined craft learned to slow. A larger vessel carried water through filters, air through leaves and machines, and gravity around a turning ring. Its clocks gathered years at whatever rate its speed allowed. Signals traveled ahead and behind. Their replies took childhoods. At the far end, 2 small confirmed planets circled the red dwarf, while a possible giant moved through the glare of a sun-like star. All of those pictures return to one simple place. Earth already has the complete life support system every starship is trying to rebuild. It has air without a pump room, water that rises into clouds, and gravity available in every hallway. A civilization becomes ready for another star by learning to care for small living systems longer than one lifetime. The departure is only the visible part. Outside, Alpha Centauri's light continues to arrive. The photons landing tonight began their crossing more than 4 years ago. They needed no shield, no engine, and no permission to finish. The room beneath that light can remain ordinary. Beneath it, the planet is turning at its familiar pace. Air moves, pipes murmur, and somewhere leaves are opening to a local sun. There is no need to cross 40 trillion kilometers before morning. Lasers can remain dark. Folded sails and careful equations can rest on their pages. Let the nearest star keep its distance for now. The only small crossing left is from wakefulness into sleep. Rest well. Good night.